we're going to look here at finding the upper bound of the travelling salesman problem by using the nearest neighbour algorithm. So in this case here, you're given a graph of lots of different set of deliveries, distance between cities for deliveries. And the key first thing is that in order to go through this process, you need a complete graph. Now, we don't have a complete graph here because everything doesn't connect to everything else. So what we do is we turn into a table of least distances. That means that we know the least distance between every point, even if it's not a direct connection. Most of that table has been given here to you. First of all, you're asked just to find the remaining points. So, for example, A is the distance between A and C. So we look at the routes we could take between A and C. We can either go this way, which has 20, or this way, which is 17. And by inspection, there's nothing better. So A is 17. As you can see, the table of least weights is symmetrical. It doesn't matter if we're going CA or AC. Then we look for point B, which is the distance between B and E. And again, we look at it we could go this way between B and E, it's 22. This way here is 21. Nothing immediately, obviously, better. So 21 is B. And finally C, the distance between D and E. There's this direct route at 21, but actually we look carefully, 6 and 13, there's a route there that is 19. So once you have your table of least distances, you can then begin to apply the nearest neighbour algorithm, telling us that we need to begin at town A, because that's where we're going to end up. So we go to our table, and initially, because we're beginning at town A, we cross out column A. Then we look for the lowest value. The lowest value in the row of A is F. So we looked across this row and we found that the lowest value is F. So we then cross out the rest of that and we can actually start to write down the route AF. Then we say, okay, so now we're at F. What is the next shortest distance? So we're just going to keep taking the shortest distance every time. So the next short distance is at G. So we cross everything out, write down G, and then we look at G and we say, where's the next shortest distance? It is E. So we cross that out, write it down and say, okay, well now we're at E. So this time 21, 16, 19, 16 is the shortest. Cross out that, we're now at C. And again, C, we're now at, we're going to cross D. D, we've got one option, we must go to B. So D, B, and then we got to go back to A, so we look at this, B to A is 11. And so that gives us the route using our nearest neighbour algorithm. That is a route we could take. So to find the upper bound in part B, we add together all of those values. So 11 plus 16 plus 16 plus 7 plus 6 plus 5 plus 5, which is 66. So that is a route. That would get us through all the points. And so that must be either the best solution or an upper bound, because or an upper bound for the best solution, because we know we can do that. We can definitely, that's a valid route. We can definitely go that distance. So anything longer than that cannot be the solution to this. But it is possible we go shorter. This is just a valid route. Now in part C, we're asked to say, well, what's the actual route there? Because remember, this is a table of least distances. So some of those values, when we go between them, they're not direct. And all we want to do is just follow through the route and see where it actually takes us. So A to F, that we can do directly. F to G, the nearest route is direct as well. G to E, and you go directly again. E to C, and we're actually going to go back to G and then across to C. So we're going to go G to C. Then we're going to go from C to D, that's going to be a direct route. D to B, again, if you think about what the most direct route was, we were going to go D to C and back to B. So D to C to B, and then B to A is also a direct route. So that's the actual route taken. And the question was, which towns would he pass through more than once? So G and C. And it's common to be asked either that, which one they pass through more than once, or what is the actual route that would be taken.